Hello, sir.
Sundar, how are you? Hello? Am I audible?
Sir, உங்களோட அன்மியூட் பண்ணுங்க சார்.
இல்ல, அன்மியூட் தான் ஆயிருக்கு.
ஆடிபிள் சார், ஆடிபிள் சார்.
சார் நீங்க
ஆடியோ வரல, வெளியே போகுது. நம்ம வீடியோ எங்க வருது?
100% ஸ்பீக்கர். சார் இங்க மியூட்ல இருந்திருக்கு சார்.
ஓகே ஓகே.
ஹலோ
சுந்தர், சொல்லுங்க சுந்தர், கேக்குது.
சரி சரி சரி. இருக்கீங்களா? கேக்குதுல்ல சார்? சரி.
கேக்குது.
ஓகே ஓகே சார். ஸ்லோ போகுதுன்னு நினைக்கிறேன்.
அதெல்லாம் அப்படிதான் நெட் பண்ணேன். இருக்கிறானுங்களே ஒரு வாட்டுக்கு சிவன் இதுவும் கூட மாட்டானுங்க. கல்வி இருக்கிறாங்க. Congratulations to Honorable Vice Chancellor for great organization of biotechnology.
ஸ்லோவா இப்பதான்
இதுதான் நான் யூடியூப்ல போயிட்டு இருக்கேன்.
பேசி முடிச்சதுதான்.
எல்லாம் நிறைய எழுதுவாங்க.
அது சாமி வாங்கிட்டு நினைக்கிறேன். சாரி
போடலைங்களா?
இல்லைங்க, நடந்துட்டு இல்லை, நான் முடியல. ஒரு பையன் உடனடி உள்ளுக்குள்ள இருக்கிறேன். இந்த
So, very good morning to all. On behalf of the organizing secretary and to the day 2 seminar on recent trends in chemistry 2021, organized by Department of Chemistry-Bharathiar University. I also thank the organizing secretary for giving this opportunity to introduce today's speaker. Scientist, another faculty university, assistant professor ACR. Now he is working as a senior scientist in the inorganic physical chemistry laboratory, CSR CLRI, Chennai. So it is my great pleasure also to read out his credits and a brief biodata. Sir started his academic career in the year 1994 to 1997 as a BSc student at Vasavi College, Erode. After BSc, he moved to Madurai Kamaraj University to pursue his PG program. So in the year 1999, he joined with the...
Would have asked the questions, why when adding something to the white color sample or the colorless samples, some colors are generated, and what could be the origin of the color, and why few molecules are colored and few are colorless. So again, everything depends on, or can be simplified like these equations, where any molecule, for example, let us take here the electronic energy levels, because when you are talking about the spectral changes that happens in the UV or visible region, so the states of the molecules which is responsible for those transitions are the electronic transitions. So for example, you define in the electronic transition of electronic state of a molecule into E1 and E2. So the delta E, which is the energy difference between the E1 and E2, is h nu, that is the energy of the photon. If the energy of the photon matches with any of the visible light photon, that is getting absorbed. So, and what you are seeing is complementary color. You can see here the green is getting absorbed by the system, and you are seeing the remaining colors. So that is actually the complementary color that you are seeing. So that's, and of course, in terms of a molecular perspective, you, for example, you take a benzene and naphthalene, anthracene, and goes on, then you are decreasing the energy level between the two states, and that means increasing the wavelength absorption. Okay. And of course, this is more important diagram that you probably might have studied, and even for any chemistry student, and those who work on fluorescence, still we will be using this diagram. Probably at least in a day, at least once in a day, I will be using this diagram. So this is such an important, at the same time, very simple diagram that will explain molecular properties. Okay. So, for example, you take a molecule, which is, let me define this molecule as a simple, like an organic molecule, where you define the states as a singlet ground state S0 and the singlet excited state S1. And once the light is absorbed by the system, it goes to the excited state and come back to the ground state. And it will be emitting the light, whatever the energy absorbed should be dissipated forever. It has to come back to the ground state. So the absorbed energy has to be dissipated back to the ground state. So either it could be that in terms of a radiative transition, what we call it as a fluorescence, or it could be a non-radiative decay, or that means the energy could be dissipated as a heat. And there is another thing, another process also called what is known as the intersystem crossing. So here the triplet state, here, for example, you say here the pair of electrons that the spin is kind of preserved here. That means both will be having a anti-parallel spin. But if the spin is flipped and it is moved to the triplet state by the flipping the spin, that means both the electrons in this place are having a parallel spin, that is called as a triplet state, where from here also it will become state by emitting the radiation. So that radiation is called as a phosphorescence. So in any molecule you can take, if you take the dissipation of energy in terms of radiation, is either it could be called as a fluorescence or it could be called as a phosphorescence. And this is second or 10 power minus 12 seconds. It depends on the system. So if you could see, what are the factors that is affecting this one, one is the hydrogen bonding. For example, you take two different systems where one is having hydrogen bonding and another one is having no hydrogen bonding. You could see the difference. For example, from one system to another system, so there is an electron transfer happens, yes, that could be seen. And the solvent polarity, that is what is the surrounding medium, that will also be having a very significant role. And whether the two molecules, that is the intermolecular interactions are there, or is there any conformational changes are there, everything is influencing this one. And nowadays, like the scientific equipment, if I could tell, everybody, including the common man, understood what it is mean, what is known as the RT-PCR, the real-time PCR, right? So it actually, because that is used for the COVID-19 diagnostics, if you could actually see how the COVID-19 RNA is identified, it is simply using the fluorescence technique. It is the same principles that has been used here, is used in the RT-PCR machines. It is analyzing the different fluorophores and then saying that whether the particular specific RNA is there or not. So now you can understand how even that is sensitive is so sensitive in such a way that even the samples collected from the people just infected, or within a day, it is able to identify the RNA of the virus. So such a kind of sensitive technique, and if you could see any of the research lab, either biology or chemistry or materials, this technique in one way or other that is used. Either it could be used as a microscopic technique or it could be used as a spectral technique. So that's such a kind of sensitive technique it is. And of course, I'm just giving you some molecular information. So you can see, as I said, environment. For example, here I took the same molecule. And you can see here this, I'm going from the hexane, cyclohexane, toluene, ethyl acetate, and butanol. The molecule remains same. You can see the color, it is covering the entire WebGR region. So that kind of a sensitivity it is. So that's why it has been predominantly used as a biological systems. So I'm giving you here some of the examples of fluorescent probes. So these are the kind of commercial fluorescent probes that has been widely used in several techniques. For example, the fluorescein and acridine orange and quinine. So all are well-known fluorophores that has been different applications. I was talking about the stock shift here, right, in the previous slide. So you can see here the difference between the absorption, which is the marked in a blue color, and the emission spectra, which is marked in the red color. You can see that how closely this is overlapped here. At the same time, so you can see here there is no overlap at all, meaning that the perylene, which is a rigid structure, which doesn't show any much difference between the ground state and the excited state. But at the same time, if you could take the quinine sulfide, this molecule, which undergoes between the ground state and the excited state, you can see here, this one. So you can see the difference between the absorption and the emission maximum. So what are the structural changes that happens between the two electronic energy levels could be identified just measuring the fluorescence. It is a very simple technique. You can just like that, you can do it. Okay. So I'm just coming back to some of my work and how the molecules can be used as a probe. Okay. So here I'm going to talk about the molecule which we have synthesized in collaboration with one of my collaborators, Li Wang and Dr. Saravanan, and we have designed this molecule. So why we have designed this molecule, particularly focusing on the fluoride? For example, why fluoride is more important? For example, you take a fluoride, the India's groundwater, I can put a news from a website here. So over 100 districts in India is having the groundwater contaminated with the fluoride. The problem, because those contaminated groundwater or the fluoride-rich groundwater are used for the irrigation or used for the drinking purpose, and so that it is in the life cycle or the food cycle of the human. And why the fluoride is important is it will causes the skeletal fluorosis or the dental fluorosis. For example, even if you could see the in Tamil Nadu, Dharmaburi and Krishnagiri area, which are having more fluoride contamination, because the presence of high amount of fluoride, so it induces the high amount of calcium intake, at the same time suppresses the iron intake. So it will causes a lot of problems, weakening the bone and weakening the enamel, creating the porous structures in the enamel, such a kind of thing. So how the fluoride could be analyzed? If you see the conventional techniques, you need to take the sample and analyze using sophisticated instrument. But at the same time, if you are having a molecule, you just, for example, the benzoselenodiazole molecule. So here it's a very simple molecule. So here we are having the NH, which is this NH proton is a highly acidic because it is having substituted with an electron deficient nitro group, and this group is also an electron deficient group. The moment fluoride is added, so it has a base and then it deprotonates the hydrogen here and it form a kind of a quininoid structure like this. So you can see here, we have taken the different anions. Only the fluoride is able to deprotonate, and the other anions, which is predominantly present in the environment, doesn't influence. So if these kind of probes are used, you don't need to have a kind of an equipment for analyzing whether the particular water is contaminated with the fluoride or not, which can straight away go with say on the field you can analyze that yes, this water is contaminated with the fluoride. It's very simple chemistry. You just deprotonate it and it form a charge transfer complex with the positive sign here and negative sign here, and then that will be giving you the intense dark color. It's a very simple experiment can do. And other one that we are have done with the probing is, I'm sorry that I'm unable to give you the structure of the molecule because the patent application is still pending at the patent office. So what we have done is the mercury. The mercury contamination, again, it is a prevalent in many of the places. So we have developed a probe for mercury, and we have gone even much advanced level. So whatever the thing that I have been claimed in the patent, we have gone at a ppm level. Now we have gone at ppt level. That is the part per trillion level. That's the reason which I am not going to present today. For example, you take different metal ions, which are of course present in the environment. You can see here only the presence of mercury 2 shows the color change from yellow to pink, and you can see the color change. This is only the fluorescent, and the other things are not a fluorescent molecule. non-fluorescent system. So this is what we call it as a TOW non-fluorescence. So here it is based on the electron transfer mechanism. So I'm not, as I said, I'm not going to the mechanisms. And of course, what we thought is, okay, so we have been, since we have been developing the probe, so what we thought is, let us increase the binding sites. For example, whatever I have given in this probe, which is actually a tri-arylamine based system. So I want to increase this is actually the probe with the one which is marked in the pink is actually responsible for binding with the metal ions. So what we thought is, okay, let us increase the number of probe molecules so that we will just go increase 2 and increase 3. So what we thought that, okay, so it will be binding with 1 mercury ion or a silver, and this will be binding with the 2 metal ions, and this will be binding with the 3 metal ions. So even the simple probe can be utilized for so this will actually increase the sensitivity. So to our surprise, so it doesn't happen. What happened is, so when we are adding the metal ions, see these probes were highly sensitive to silver and mercury. So you can see here the difference. Even of course, if you could see this images that I have given, so you can see that the difference in color observed for mercury and silver. Even either if you could see by the naked eye, or even you could see under the UV excitations. So you can see a blue fluorescence for mercury and pink fluorescence for silver. So these kind of specific or discriminative detection of silver and mercury can be done. And if you could look into that actual thing that is happening is what you call the simple HSAB concept that we have studied during the postgraduate level. So these ligands these systems are having a sulfur group, so which interacts with the mercury and silver through HSAB concept, soft acid, soft base concept. So which are more selected towards only the mercury ion. The interesting part here is that it gives a distinctive signal from silver and mercury, which is otherwise actually the same signal for the silver and mercury. Sometimes it will not be, one will not be able to distinguish between these two systems. And another thing that we have observed in this case is that what we, as I said in a little while ago, that both the things are whether it is binding with the 2 metal ions or whether this is a binding with the 3 metal ions. Unfortunately, all the 3 systems are binding with the same metal ion. I mean, only 1 metal ion and not for 2 and 3, irrespective of the number of receptor groups that is having. So when we are analyzing the further why it has not been happening. So once the metal ion is interacted with this one, because do remember that this is a kind of a completely conjugated system, it forms a complete charge transfer kind of complex with the metal ions. So ultimately, this after complexation of the first metal ion, the second metal ion environment is totally different, so that it is unable to be available for binding with the other metal ions. And this we have published in ACS Sustainable Chemistry and Engineering last year. And there is one more important thing. Many people often being confused between the photochemistry and photophysics. So they say it is a photochemistry, sometimes it is actually the photophysics. So the difference is actually, for example, you just recall the previous beginning slide. So if you are able to retain the molecule after excitation and the molecule come back to the original state, it is actually the photophysics. There is no chemical occurs. The molecule goes to the excited state, give up the energy either in terms of a radiative or non-radiative decay, and come back to the ground state still with the same structure. That is actually the photophysics. And the photochemistry is actually the molecule goes to the excited state. From the excited state, it undergoes a permanent structural changes. For example, in this case, a cis-trans isomerism, and then come back to the ground state. So that is actually the photochemistry. And for example, if you could see the molecule which shows dominant photochemical pathways, for example, you take an azobenzene, its photophysics is very poor. That means it will not be fluorescing. All the energies it is absorbing is actually using for the chemical isomerization from a trans to cis isomer or either cis to trans isomer. But at the same time, it doesn't show any photophysical behavior. So these processes are kind of, if one exists and the other doesn't exist. So what we thought is whether we could play between these two so that we make a situation in such a way that at some point photochemical pathway and facilitate the photophysical pathway. In fact, this is actually the brainchild of my student Raman, who actually conceived this molecule and then he synthesized. And of course, though molecule looks very simple, and it took a lot of time for us to figure out what is actually happening with this molecule. Okay. I'm not going into the mechanistic details. So what I'm going to talk about is how it could be used. For example, this molecule, which is actually coupled with the rhodamine and azobenzene. And if you could see here, this is a kind of a spirocyclic system. And when in a pyrocyclic system, it is a non-fluorescent in nature. And we have coupled with here, and of course, conjugation will be there, but at the same time limited because it has a biphenyl configuration. So what happens is that once aluminum or any metal ion is added, it will go and bind with this place, and then the spirocyclic ring is open and it will be made into the spirocyclic ring is converted into a conjugated bond with sp2 carbon here, so that the conjugation will be there, so it will be fluorescent. And then we are shining the light. So whether in this case, so when we are shining the light, the thing is that whether this will be responding. So that was the question that we have been having. So for example, this one, you take the first one, yellow color, then you are adding an aluminum 3+, and then you can see here there is no much changes. And if you could excite this one using a 365 nanometer, you can see an intense flow, intense kind of out of this molecule. So this experiment we just did in terms of the 365 nanometer UV light. So what we did is that you just add an aluminum and see whether the color change is there. If you could, what we have observed is there's no significant color change after aluminum. For example, you can see here the absorbance spectra that you can see comparing the black and red, you can see not much changes. The moment it is shined with the 365 nanometer, you can see that it is increasing. Actually, the light is catalyzing this reaction, and simply I can say that it is amplifying the signal. So these kind of signals or these kind of molecules are important when you are considering the biological applications. That means you can selectively target a particular place and shine the light so that you can amplify the signal at the places where you want, not the places that not all the places. And of course, I'm not going to the mechanism, so this also I will skip here. And this is another example. With the same system, we just modified the structure a little bit. So this is the beauty of these molecules. We have been using the azobenzene in the previous case and the rhodamine in the previous case, but we just changed the linker a little bit here, and the entire chemistry is changed. For example, in this case, it is so selective for aluminum 3+. The moment you modify the structure to little extent, and then it is selected towards iron and not towards the aluminum. So that is the thing. So here, what we call it as the rotor unit, motor unit, it is actually, you can call this as kind of molecular machines. So here also the same principle is applied, but the only difference here there we are talking about is a throw bond energy transfer. Fluorescence resonance energy transfer. Here the mechanism is through throw bond energy transfer. You can see here, so with simple addition of the iron 3+ doesn't happen. So when we are shining the light, the intensity is becoming increased, and you can see that without irradiation, you can see here it is everything is a kind of flat, and then within irradiation it increases. Of course, aluminum do respond in presence of light to some extent, but it is dominated by the iron 3+. So this work we have published in the Journal of Material Chemistry C. Okay. So far what I have discussed is actually the spectral changes when I was discussing about the Jablonski diagram, I said that the lifetime of the system, that is how long the molecule stays. Conversions which happens in the sometimes femtosecond to picosecond time scales or picosecond to nanosecond time scales. It depends on the molecule to molecule. And the vibrational relaxation against the picosecond range and intersystem crossing little longer, and it takes from like a picosecond, nanosecond time regime. So whether these analyzing, if we are able to analyzing the time constants, then it would be providing more information. Why this is more important here is one of the drawback that fluorescence technique has is it is not like a quantitative one. For example, you take an absorption spectrum. It is governed by the Beer-Lambert's law. The absorbance equal to epsilon and Cl. Epsilon is a constant, the molar extinction coefficient, concentration, and the path length. So it is governed by the Beer-Lambert's law. You just measure, and you can straight away use those values for quantitative estimation. It's not applicable for the fluorescence. It is not it cannot be used for a quantitative one. So whatever the fluorescence that techniques or the fluorescence that has been used, it is used as a qualitative one, or some reference point need to be made so that it can also be made into a quantitative one. So under those drawbacks can be overcome if you are using this kind of little sophisticated analysis, that is time constant or the fluorescence lifetime analysis. Okay. So before going to that, I'm just giving you the probably the first time resolved observation in the history. This is an interesting story. Actually, the Stanford, the founder of the Stanford University AC, so he's actually an industrialist and a multimillionaire. He was having kind of horse race academy or the organizations. So he had a doubt at some point of time, all the four legs of the horses are in the air, or all of them will be or at least one or two or three will be on the floor. So he had the doubt. So he have asked the photographer, the well-known photographer that by that time, Edward Muybridge, so whether he could help him something. What he did is then he put a series of cameras in a serious way, and then he was trying to capture the motions of the horses in a very short time scale. So for example, if you could take about the shutter speed, probably comes on the millisecond or even sometimes sub-millisecond time scale. So you can see here, these are the photographs that are taken at a different time scales. So where you can see here at least two places where all the four legs of the horses is in the air, or on other times, and even then that even the projection of the horse, the legs, are kind of different with respect to the different time. So this is actually the a representation of the actual experiment. You can see here the series of cameras are kept here, and they are triggered electrically, and you can see here how all the images are there, and the resolution of the image that has been is kind of millisecond, 0.001 second, and of course this has happened in the 1877. Okay, so this is probably the time resolved observation. Okay, so it is okay for a molecule to see those things. But the big objects like horses to see using a digital camera and see those things. But how it could be done for a molecule? And before going to that, I'm going to talk about, I would like to highlight about what are the time scales that has been used for a spectroscopy. So for example, you take the humans, of course, it's a 50 million years, and the chemical kinetics, that is the rate of the reaction, which is actually between 1852 and 1900, and stopped flow method, which is actually between 1942 1923. Actually, the stopped flow is the method you can go in a millisecond time resolution, that is 10⁻³ second time resolutions. And of course, a much more sophistication, that is the microsecond, came in 1953 and 1940 by George Porter. and he got a Nobel Prize for that. And after the invention of the lasers in 1960, this field has been phenomenally grown, with going at the picosecond with 1970 and femtoseconds with 1980. And even now the autochemistry is known in few places where that is the reactions happening in the 10 power minus 18 seconds. Okay. So this I have explained already, so I'm just going. So what we are going to talk about in the time dissolved emission is all these processes, whatever I'm talking about, the exciteplex, that is the complex formed at the excited state, the dimers formed at the excited state, energy transfer, electron transfer, conformational changes, everything has been dissolved and can be related with its own time constant. So that will be giving you a very good information. Okay. So I'm just skipping those things. Sorry. Yeah, you can see here what are the time scales that you can see here. The excitations happens at the femtosecond time scale. If you see the isomerization, it is happening at the femtosecond time scale. The best example is the rhodopsin, that is the receptor which is present in our eye. And you can see that internal conversion, fluorescence, and everything has a time scale. If you are monitoring at a particular visual process, and do remember that no single technique can cover from this region to this region. So if you want to cover this region, the technique should be different. And if you want to cover this region, the technique should be different, and so on. Okay. So how it could be done? Very simple thing. I'm just going with only the cartoonic representations. For example, so initially, let me say that I have kind of 120 molecules or something like that. Once I'm shining the light, you can see that those which are marked in the orange are at the excited states. So then at some point of time, this 64 excited state become a 32. You can see here the 32 is emitting here. And the 32 becomes like a 16, that is 64 becomes 32 excited state and having 16. And you can see that the intensity at different times has been come down. This is how the lifetime is calculated. I'm not going into the detail. I will show you an example. This is what the example. So what we have done is that we took a molecule. So we want to use the fluorescence property to probe the temperature. For example, when you want to probe the temperature, you just need to have a thermometer. And thermometer, you cannot be always thermometer. For example, and nowadays, even because of the COVID time, many people are moved to the non-contact thermometer, right? Using an IR thermometer. But whether IR thermometer also have some issues. So whether some color-based molecule, for example, luminescent probes could be developed to monitor the temperature. So what we did is we developed a molecule, so which contains like three triphenylamine groups and one acceptor group. So what we did is that we changed the temperature from one end to the other end. And of course, I'm not just presenting the lifetime. You can see here the lifetime at one of the wavelength, it remains constant. You can see here it doesn't change at all. So we are covering almost a wide temperature range, that is the above room temperature, that is 330 Kelvin or 60 degrees centigrade. You can see, 30 degrees, 60 degrees centigrade, and it goes up to 170 Kelvin. So it's a wide temperature. You can see no changes happening here. But at the same time, you can see here there is a temperature change, like fluorescence lifetime changes with respect to the temperature. And at some temperatures range, you can see here there is a straight line. You can see this is a straight line. This falls on a straight line. So at some point of time, it could be used. It has a linearity with respect to the temperature. So we can say that this could be used as a luminescent thermometer. And particularly, this is more important when you are considering the biological applications. So you cannot be measuring the cell temperatures, or what would be the temperatures at the different at the cytoplasm or at the nucleus or different organelles. So you cannot use the normal thermometer to measure those things. So in such cases, these molecules are kind of handy to help you to identify the measuring the, say, internal temperatures of the biological samples. Okay, this is actually another thing. the lifetime can be just like a fluorescence microscope. The fluorescence lifetime imaging microscope is also existing. So you can see here that the problem with the fluorescence is that even it is, for example, you take a tryptophan in any in proteins, the tryptophan and tyrosines are actually the aromatic amino acids which emits the fluorescence. So if, for example, a protein contains 5 or 6 tryptophans, and all the 6 tryptophans will be presenting in the different environments. If you are measuring this simple spectrum, you will not be distinguishing between all the 6 tryptophans or tyrosines. But if you are able to measure the lifetime, you will be able to distinguish all the 6 life residues in the protein. So that's what it is happening here. So here, only one molecule is probed, but at the same time, the molecule is having a different lifetime depending upon its environment. You can see here the fluorescence lifetime of 1.5 nanosecond is marked in blue and green, and it goes on with the lifetime, increasing the lifetime. Then you can see the color has been changed gradually. You can clearly see all those things with a high resolution, but this could not be possible with a simple fluorescence microscope. So the lifetime imaging is providing a much more sophisticated information, much more precise information about your sample, particularly for the biological system. So this is actually, again, the cat eye image. You can see here, each and every can be identified using the fluorescence lifetime imaging microscope. I'm just highlighting only the applications. Okay. So this is, moving to another topic, what is known as the multi-photon absorption. So before I'm going to that, I'll take a little time with respect to this one. Actually, this is initially, this concept has been proposed by Maria Goeppert-Mayer. In her thesis, she described that theoretically, the absorption of 2 photons is possible. That is during the 1931. And of course, her story will be interesting. So for want of time, I'm just skipping it, that at some point of time, see, her contributions are phenomenal in terms of a science, either in terms of the nuclear structure or in terms of the 2-photon absorption. And of course, she went on to get a Nobel Prize for her work in the nuclear structure. But till the fag end of her career, she was working without any regular position or without any regular salary. So that is the kind of irony of the life. So I'm not going to the details. I would recommend that please refer the Wikipedia page of Goeppert-Mayer. It is truly inspiring. Okay, so let me come to the phenomena that happens. So for example, you are defining the ground state and excited state. Probably throughout my talk, only I am restricting between the 2 states, the ground and excited states. And for example, if the energy difference is corresponding to 400 nanometer, a 400 nanometer can make a transition from ground state to excited state. But if I am able to give 2 800 nanometer photons, that is the summation of the 2 800 nanometer photon is equal to the 400 nanometer. Do remember that this is a wavelength scale. Okay, so what would be the difference? So anyway, you are making a transition from the ground state to the excited state, and doesn't matter whether it matters whether it is a 1 photon or 2 photon. So for example, you can see I have given the 2 processes here. So the one which is I am marking here, that is happening in the single photon. That is 1 photon, what you call it as. So the moment the light enters into the sample, the molecule started absorbing the light, and as it travels through the solution at fag end of the sample, the light is not available for the molecule to absorb. Okay. So for example, you consider this as a tumor cell, or consider this as an organ where the tumor is located here. You want to treat the tumor using a light, and with a light activatable drug. Okay, the drug binds with the tumor at a particular place, let us say the place, and you are shining the light, you are shining the 1 photon, the light transmits through this, and then by the time it reaches the tumor, the light intensity is not available. It will not be, or in sufficient quantities rather. So it will not be activating the drug. So ultimately, it doesn't give any, it is not a fruitful, or it becomes an inefficient. Okay. And the other thing is that your biological system or skins or any biological system should be transparent to that. But generally, the biological systems are not transparent to the visible light. Okay. So what happens with this process? For example, you can see here this process, that is the same process happens, but this will be occurring at only this place, not this place or not this place. So you can choose actively focus. For example, you say this is an x-axis, then it is the y-axis, and this is a z-axis. And the x, y, and z-axis can be focused with this two-photon absorption phenomena and not with the one-photon absorption phenomena. So this is the advantage in terms of the processes. So, and one more thing is that the 800 nanometer, which is actually falling in the near infrared region, is highly transparent for many biological systems. So that means the penetration of the biology into the human body or any biological for this one and not for this one. So it could have a wide range of applications, a wide range of advantages over this visible light. Okay, it's very simple. As I said in the previous lecture, previous slide. So you can see here, this is one photon excitation using a visible laser. You can that it started absorbing the light. By the same time you are at these places, it does nothing. And the excitation volume is more here. You can see it's a huge. Sometimes if you are imaging, for example, you are going this excitation volume, you will not will reduce the resolution of the images. At the same time, you are having a two-photon excitation, where in a near-infrared laser is used. You can see here the excitation volume is 2 minimum, and it will be giving the minimum excitation volume giving you the more resolution. Okay, so you can see I'm just giving you the visible photograph where you can see here the difference between the one-photon absorption, where all the places it is showing the signal, but here you can see at least one place. This is actually the zoomed part of this one. You can see at least one places. So you can move this place, this can move up. So it can be done in any way just by moving the focus point. And of course, these things we have done are played during our childhood days. So this experiment, many of this, I would call it as an experiment. Many of us would have been done using a paper and a lens and focus the sunlight on the paper. And just generally what we do is we just move the papers up and down. But at some point of time, the paper started burning. That means the moment where all the lines, the maximum of sunlight is focused on the paper, right? Then the paper started burning. So this is the experiment what has been done in this case as well. For example, this is actually the setup, and this is actually the place where you are moving the lens. Of course, in this case, you can move either the lens or the paper. Actual experiment in this case, the sample, and of course, there is the paper is moved. So here, this is actually a delay stage where the sample is mounted. The sample can be moved here or there. And the experimental setup is also looks quite simple. For example, a laser need to be there, and attenuators are of course altering the beam intensity, and a mirror to divert the beam towards the sample, and a detector. And one of the beam has to be moving towards the reference detector. We just move the sample here and there. At the focal point, the light is absorbed by the molecule, and the detector sees less light. So which is actually amount of light is transmitted from the source after the sample. And of course, this technique is more popular in microscopy rather than spectroscopy, because it has more application, more kind of widespread applications in microscopy. For example, I'm just here comparing the 3 different microscopic techniques. One is the wide field, and the other one is a confocal, and the other one is two-photon. If you go from the wide field to confocal, there is a pinhole is introduced into this system. You can see here the pinhole is introduced so that it is avoiding many of the photons signal, and it is improving the resolution from going from the wide field to confocal. But at the same time, going from the confocal to two-photon, so you can see here the focal plane, and you can see you can read here that is a femtoliter focus volume. That is a very minute focal volume, and you can see that you just move the focal plane from this plane, this plane, this plane, this plane. You can imagine all the planes. That means it will not give you any information about the depth of the samples or what happening in the few layers below the surface, but this will be giving you even up to 8 mm of depth. This is one of the examples, multi-photon microscopic image that has been scanned for the rat brain. So molecule is very simple. You can see here it's naphthalene-based molecules. Once in the presence of hydrogen peroxide, and then it has been converted into molecules. So the intensity, the fluorescence spectra are different for these two molecules. And of course, the hydrogen peroxide is very important species in terms of physiology, and which it is associated with the aging, disease, etc. And you can see here that is the fluorescence intensity is proportional to the amount of hydrogen peroxide generated at a particular layer. The numbers that is given is 90 and 100 are actually the depth of the mouse brain. You can see here the fluorescence intensity is changing with respect to going from 90 micrometer and going down to 100 till 180 micrometer. You can see here that in between the intensity is quite high. So meaning that the hydrogen peroxide is generated on those layers. So this could not be done with the simple fluorescence technique using visible light radiations. And this is another example of creating or generating the microstructures or the nanostructures. The problem with the microstructures or the nanostructures is that handling using either the human hand or even the robotic hand, because the handling of such a kind of a small objects are not an easy, and the precision will not be that much quite good when it is handled by the human or the robotic hands. So in that case, that mechanical operations cannot be done. Here, this 2-photon polymerizations can be done. You can see here these objects that has been generated are some of the prototypes, heart valve, or even some of the insects, or very small, tiny arts, which are in the range of a micrometer. You can see here that the entire dimension is actually the 40 micrometer. And these objects are, you just focus the light on this sample, and then it will induce the polymerization. It's a simple polymerization reaction, and such a kind of sophisticated objects are generated. And this is also used for micro and nanostructures. And of course, this is actually another video I just want to, I don't know whether, So you can see here, this is actually the 5-dimensional optical read on the fluorescence techniques. We thought that it's fluorescence just only ends up with the fluorescence spectrophotometer, but it is not. So for example, this is 5-dimensional imaging, where you can see here these each layers are stored with different images. And do remember that this here, the polarization, fluorescence, and another important property that I have not discussing today is the polarization. So either it could be the vertically polarized or the horizontally polarized. You can change the polarization so that you can just make them as invisible one. So I'm just, you can look into the video and you can see that in layers, this is actually the perpendicular position or the vertical position. You can see one image. Now it is moved into the horizontal position. You can see another image. So this is actually the one layer. It has, these images are stored. You just move into the next layer. You just watch the arrow. It's just move into the next layer, and different images can be stored. So these techniques are quite important when you are talking about storing the confidential documents, particularly for the strategic sector like a defense. So where nobody knows where the data is stored or how the data is stored, even it has been in the wrong hands, no one can realize such kind of security it gives. And more than that, it will also increase the the storage density. So the single CD can store up to 500 GB of data. Now it is almost like a 14 GB or something like that. It could be increased to 500 GB of data. The optical and data storage density could also be increased. So these, of course, these are the molecules which I have used for studying the supramolecular assemblies for the 2-photon absorptions. So I'm just quickly go through this one. For example, here the problem for the 2-photon absorption is that the efficiency. It's not like the 1-photon absorption where even the small molecule will give you the good results. But here the efficiency to increase the efficiency, you need to have a much bigger molecules. For example, if you are using a simple porphyrin systems, it doesn't give anything. But at the same time, you increase the number of porphyrin systems, then it will be the efficiency will be increasing. So I'm not in here. Of course, no, there is one interesting point that accidentally we found during this one. So as I said, that increasing in the conjugation is important for the 2-photon absorption property. So we have increased the conjugation in one dimensional. We were able to see that the 2-photon absorption is increased. But at the same time, we increased the concentration in the other dimension as well, the second dimension. And of course, if you see overall 2-photon number of porphyrin units, here from trimer to pentamer, the number of porphyrin units are at least, more. But you can see it has been this is more efficient than this one. It is because these two are kind of competing with each other. It's quite an unusual results that so these two are competing with each other, and this is a kind of what we proposed is not only the number of units, it is the dimension of the molecule is also an important thing. And of course, this one and probably I'll just. I'm just giving you the introduce the molecule and then I'll just probably skip. And this is a kind of not an much developed or much explored molecule. That is what we call it as a subporphyrin. Porphyrin, you are having a 4 pyrrole rings and an 18 pi an aromatic system. But here it is 14 pi. You remove one of the pyrrole ring and make 3 pyrrole rings, and it is in a 14 pi aromatic systems because you are removing one of the pyrrole ring, and then the structure is not a kind of a planar structure. It is a kind of a bowl-shaped structure, as you can see. And one problem with the porphyrin is, and whatever you substitute at this position, this is actually the meso position. Substitute at this position, you will not be having any impact on this electronic properties of a porphyrin ring. But here, it is a kind of a planar structure, bowl-shaped structure. So whatever the thing that is happening with the substitution at these aromatic rings, it is highly reflecting on these electronic properties of the subporphyrin. This is a kind of a new class of chromophoric unit, but still a lot need to be explored. The reason being is the synthesis is a kind of a tedious, or I can say the yields are very minimum, sometimes 2%, 3% yields are obtained. So that is the one disadvantage with respect to this molecule. Otherwise, at some point of time, these molecules will be kind of overtaking porphyrin in terms of applications. Okay, so with this, these are some of the examples that we have discussed. Even for example, here the 2-photon absorption cross-section efficiency, we just got few thousands with so many big molecules, like a 4,000 big molecules. So the same thing has been accomplished with a very small molecule like this. So it doesn't mean that a proper choice or proper design of a molecule is quite important. And of course, this is again the recent example, the tumor-specific fluorescence imaging, where particularly the cancer cells, ovarian cancer cells can be identified using this kind of a dye linked with chiral compounds, where it goes and specifically binds with ovarian designing this molecule. I'll show you how the surgery done in this video. You can see here. So you can see here, the surgery is ongoing, and they were able to see the bright luminescent spots of the patient. So those cells are actually kind of plugged and removed so that no cancer cell is left in the body, so that the recurrence could be minimized. So you can. you can see here the bright spots, which are actually the cancer cells where it can be plucked and then it can be removed. Otherwise, it would be difficult for the surgeon to see. You can see this is actually the fluorescence image. So this is using a near infrared excitation. So doctors are removing those cells so that it is a kind of complete removal of the cancer cells from the body. Okay, so with this I'll just conclude. As I said, the fluorescence is a kind of quite sensitive technique. You don't need to have much amount of compounds. Even a few milligram compound is enough for even doing a PhD work. And the work what I have presented is actually supported by the CSIR CLRA and the funding from DST through SCRB as well. And collaborators for either in molecular synthesis or even for the biological imaging. So Dr. Nandakumar of Karunya, Ayadurai of CLRA, and Professor Lee Wang. And these are my students who are actually the soldiers of carrying out these works. So thank you very much for your attention. So if you have any questions, then I'm happy to answer. Thank you.
Now the session is open for discussion. If anybody have any clarification, you please ask Dr. Iswanamurthy.
So probably every.
Sir, good morning, sir.
Please.
Sir, we had a question in Google Meet.
Yeah.
The question is very nice and high information. The bowl-shaped tripyrrole boron system. Clarify on this. This is the question, sir.
So what is the tri?
The bowl-shaped tripyrrole boron system contains 16 pi electrons. Can you verify on this?
No, it is actually 14 pi. Yeah, it's a very good question. Yeah, often people confuse. So I'll just put the slide again. Even for same thing happens for porphyrin also. So there is a double bond here. But it has been, when we are calculating for an aromatic thing, it has not been counted in the sense that the pi conjugation cannot be going in all the directions. It will be kind of unidirectional. It will be going like this. Okay. So the same way, one of the double bond here is not counted or not accounted, not participating enough in the aromatic character or the pi conjugation. I mean, overall pi conjugation. So that's why the 14 pi electron is the correct one. So here also we are saying 18 pi electron, but actually another 2 pi electrons, two more pi electrons will be there. It has not been counted. Okay. It's a good question, good observation. Thank you.
Thank you, sir.
Okay, in the absence of any other question, it is time to thank Dr. Iswanamurthy for his extraordinary and enlightening discussion about the luminescent molecular probes. By the way of explaining basis of emission from the Jablonski diagram too, he explained in a very nice manner. On behalf of organizing committee and chemistry department, Bharathiar University, we do thank Dr. Iswanamurthy for his finest talk to discuss with the audience. Thank you very much, sir, for your contributions and discussions. Thank you very much.
Thank you. Thank you. Thank you for your attention. Thank you. I can leave.
Thank you, sir.
Thank you, sir.
The participants, please note, next session is at 2 p.m.
Please note, next session is at 2 p.m. to 3:30 p.m. And the speaker is Dr. Shanmugam, functional materials and coatings for PV, and join us on Google Meet by 1:45 p.m. Those who are unable to, please use YouTube link.
Also, make sure to fill
the feedback form and submit before 2 p.m. Thank you.